benzene ring, any incoming electrophile will predominantly react at the ortho position. That's what it means. And whenever we have a carboxyl already in the benzene ring, and then we react this benzene ring system that is already substituted with another electrophile, that electrophile will predominantly react at the meta position, or at position 3, relative to the position of the carboxyl. That's what it means. So you can see 80% of the meta-substituted product is formed, and almost nothing of the para, and very little also of the ortho. So we say that the carboxyl in this case is predominantly meta-directed in terms of an electrophile that is going to come after it is already installed onto the benzene ring. That is also the same with the cyano and also the nitro. Okay, so carboxyl, cyano, nitro, these are meta-directed. Okay, predominantly. We are not saying we are not going to get any product of substitution at we are still going to. Okay, so is this the battery issue that still mentioned? Okay. Yeah, I think it's a battery issue. I can see this.
Trying to screen.
Okay, so thank you very much for that assistance. So we see that the carboxyl, cyano, and nitro, in short, remember the carboxyl is quite electron withdrawing. The cyano is also electron withdrawing, Cn. That is quite electron withdrawing. The nitro is electron withdrawing. So electron withdrawing groups, we are able to identify them via the presence of electronegative atoms, nitrogen and oxygen. So even in the carboxyl, we have 2 oxygen atoms. We also have an oxygen atom in the methoxy, but we are going to see that there's a second effect. We know that oxygen is electron withdrawing, but because it has a lone pair of electrons, when it is directly bonded to a benzene ring, it can also donate electrons via resonance effect. And the resonance effect tends to outweigh the inductive effect. So because of that, the methoxy is overall electron donating, or it makes the benzene ring electron rich. But that is not the case for nitro. It is not, the nitrogen here does not have any lone pair of electrons in the nitro. So it doesn't donate electrons to the benzene via resonance effect. So even here, the carbon does not have any lone pairs of electrons to donate electrons via resonance effect. So we are saying these are electron withdrawing. Even the carboxyl is electron withdrawing. The methoxy is has that oxygen which we know as electron withdrawing, but at this, in terms of inductive effect. But at the same time, that oxygen also has a lone pair of electrons which can be donated into the ring system via resonance effect. So we are going to talk about these so that we can try to explain why the methoxy, methyl, chlorine, bromine will favor ortho-para substitution, while the carboxyl, cyano, and the nitro will favor meta-substitution for the incoming electrophile. Okay, so this is what this particular slide is trying to put across, certain substituents direct preferentially to the ortho and also para positions, others to meta positions. And substituents are classified as either ortho para directing or meta directing toward further substitution. So let's look at specific examples here. On this particular slide, what we see is a specific example of anisole. Now, anisole is a common name. It's a trivial name for this particular compound. Otherwise, the actual name is methoxybenzene, the actual UPAC. That is methoxybenzene. Okay, or phenyl ether, or phenyl ether. So this one reacts with nitric acid in presence of acetic acid. Nitric acid being the source of the nitro electrophile, or you can equally use sulfuric acid, which is going to react with nitric acid in order to form the nitronium ion. So we see that nitroanisole is formed in 44%, and then para-nitroanisole is formed in 55% yield. The situation is different when we use benzoic acid now, which has that carboxyl group that has different directing effects. The carboxyl is a meta-director. So because it's a meta-director, nitration here will predominantly occur at the meta position. So we see 80% yield for the meta product. So in short, if you have, for example, if you have, for instance, 100 molecules of benzoic acid, about 80 of them will react to form meta-nitrobenzoic acid, and then about 18 of them will react to form orthonitrobenzoic acid, and then the rest, about 2 of them, just 2 out of 100, will react to form para-nitrobenzoic acid. So we see that overall, the carboxyl group attached to the benzene ring is a meta-director, okay, because it tends to direct the incoming electrophile to the meta position. So that is very important. And we have another example here where if we wanted, for example, to make para-nitrobenzoic acid, if we wanted to make para-nitrobenzoic acid, which is that particular compound. And then we start by, first of all, reacting this methylbenzene with nitric acid, a mixture of nitric acid and sulfuric acid. We are going to get this intermediate, that intermediate which has a nitro at the para position. And then we can oxidize the methyl with potassium dichromate, which is an oxidizing agent. You can see that hydrogen atoms are being removed from the carbon, and then oxygen atoms are being introduced. Potassium dichromate is an oxidizing agent, so it's able to oxidize the methyl by removing hydrogen atoms and then replacing with oxygen atoms. Oxygen atoms get bonded product because the carboxyl is a meta-director. So if you carry out this transformation from the methyl, predominantly what you are going to get is meta-nitrobenzoic acid. You are not going to get 0 completely, but you are not going to get 100% full mass because it means that you've forgotten. If after carrying out this step, you put this nitro here, and if you understand that the carboxyl is a meta-director, maybe you are even going to indicate that this is minor minor product. Okay? But if you indicate that this is major, then you are clearly demonstrating a lack of understanding on the directing effects of different substituents. The most ideal route to synthesizing para-nitrobenzoic acid is the top one there, okay? Because with the methyl already installed, that we know that one is an ortho para director. So it's going to give us the para intermediate in very good yield. And then that is followed by oxidation of the methyl with potassium dichromate that is acidified in order to get para-nitrobenzoic acid. So this is how directing effects. This is just an example. There are many, many other examples of how the directing effects of different substituents are utilized in synthesizing organic molecules. And you actually try to use these principles. So a good medicinal chemist, one that is trying to make a certain drug molecule, will not even mix certain chemicals because that will amount to wastage of money before they can understand these principles. So let us now look at why is the carboxyl a meta-director? Why is a methyl an ortho-para-director? Why is a cyano and also the nitro a meta-director? Why is a chlorine and bromine? Why are these ortho-para-directors as well? So we are going to look at the theory of directing effects. Okay, so that is what now explains these directing effects between the reacting substituted benzene and also the incoming electrophile. One thing that we need to understand is that the slowest step in electrophilic aromatic substitution of benzene is the addition of the electrophile. The first step, which is the attack of the pi bond in the benzene, because that involves the disruption of the very stable aromatic system. So that one has a high activation energy, and therefore it is the slowest. So that is the slowest rate determining step in electrophilic aromatic substitution. And we are going to see that this slowest step, which leads to the formation of a carbocation, or what we call an arrhenium intermediate, because it's coming from an aromatic compound. It is actually what holds the key in understanding why certain functional groups are meta-directors and why others are ortho-para-directors. So for almost every electrophilic aromatic substitution, the rate determining step is the attack of the electrophile. The reason is simple, because that step involves the disruption of a very stable system, the aromatic system itself. Okay, and that tends to give the resonance stabilized carbocation, or the resonance stabilized cation intermediate, which is further reacted by the removal of a hydrogen atom, which is being substituted in order to regain aromaticity, in order to regain that stability associated with the aromaticity. So, the more stable the cation intermediate, the faster the rate determining step. Okay, it's very important for us to understand that. We saw this with SN1 reactions as well. The more stable the cation intermediate, the faster the rate determining step, and the faster the overall reaction. For ortho-para-directors, meaning those substituents that direct the incoming electrophile to the ortho and para position, the ortho-para attack, okay, when an electrophile attacks the para or ortho position, that actually leads to a more stable cation than the meta attack. We are going to see why. Okay, why should a more stable cation be obtained when a benzene ring is substituted with another substituent, but a less stable cation is obtained when benzene is substituted with another substituent? Why should a more stable cation be obtained when we already have a methoxy, which is already substituted on the benzene ring system? Why should we get a more stable cation when an incoming electrophile attacks the ortho, but get a less stable cation when an incoming electrophile attacks the meta? Why should that be the case? And also, why should attack by an incoming electrophile lead to a more stable cation when an incoming electrophile attacks the meta position for a benzene ring that is substituted with a carboxy? But when the same attack happens on the ortho or para, for a benzene that is substituted with a carboxyl, a less stable carbocation is formed. Why is that the case? So that is the question we are going to try to answer. So in the case of ortho-para directors, the attack that forms a more stable cation is one that happens on the ortho and also the para position. So these are formed faster. The activation energy for the attack on these positions is actually much lower, and therefore these are formed faster than meta products. We are going to see why structurally now, because this is not enough. Just describing this, in organic chemistry, this is not enough. We need to see structural reasons why a certain carbocation is more stable. Is it connected to, maybe electron donating groups that cushion that positive charge? Those are the effects we are going to be looking at. Or is the carbocation sitting on a carbon that is connected to an electron withdrawing group, thereby making it more unstable? So those are the effects that we are going to look at. And then the same holds true for meta directors. For meta directors, okay, so we have to understand this was as in directing effects, not directing effects of the substituent. So the meta attack will form a more stable cation than an ortho-para attack. And in this case, the meta products are formed faster than ortho-para products. So let's look at the ortho-para directors. Okay, the methods itself. This is an ortho-para director, meaning when methox is already present in a benzene ring, and then we react that benzene ring with a nitro electrophile, the predominant products we are going to get are the ones where the nitro attacks the ortho and also the para. Okay, so you see that this is a normal step that you are familiar with the pi bond of the benzene ring breaking up. So let me just try to sort out this. Okay, so I think this has to do with the HDMI cable, this one, right? It seems to be loose. But anyway, we can continue because, of course, even though it is disrupting the visibility, but we are able to see. Okay, so the first step is electrophilic attack. The pi bond on the benzene will break, and then that is the nucleophile attacking the electrophile NO2+, that is the electrophile. That is the slowest step, and it is therefore the rate determining step. Okay, so once that happens, in this case, if the nitro was to attack the meta position. Okay, if the nitro was to attack the meta position, this is the intermediate carbocation that would be formed. Okay, we are trying to see why attack at that position is not favored for a benzene ring system that already has a methoxy. And then you can try to draw the different resonance structures, remember. So this is a resonance stabilized carbocation. That pi bond can shift, and then the positive charge goes to that other carbon, and then this pi bond can also shift, the positive charge goes to that other carbon. Then finally, we get the final product. So we are going to try to compare this set of resonance structures, the three of them, with another set of resonance structures that are likely to arise when attack occurs at the meta or ortho position. Not at the meta, but at the para or ortho position. Yeah. So this is, someone is calling, but I can answer that at a later stage. So, yeah. So let's now try to compare, let's try to compare these set of, so the answer, the idea behind this, when I ask you to explain why meta substitution is, okay, let me just cut them. I hope they don't go again. I'll call back at the later stage. So when I do to explain why substitution occurs predominantly at a certain position, the best way to rationalize or to explain is to look at the resonance structures of the intermediate carbocations. Okay, that is where the answer lies. So let's look at, so this is attack at the meta position. We only have 3 resonance structures for attack at the meta position. And remember that the more resonance structures you can draw, the more distributed the charge is, and the more stable the carbocation. Okay, so let's now try to examine attack at ortho or para. Okay, so attack at ortho or para will lead to the formation of this carbocation here. Okay, and now you can see that you can draw, you have 4 resonance structures here. Okay, so you have 4 resonance structures here. The more resonance structures you can draw, the more stable the carbocation, because the positive charge is distributed over many, many atoms compared to the others. So we see in this case that even now, the oxygen atom is actually able to stabilize the positive charge via resonance effects. Okay, so it contributes its lone pair of electrons into the ring system, and therefore it is also able to bear or accommodate the positive charge. That wasn't the case in the previous one. We can try to go back. There's no opportunity in this case for the oxygen atom to stabilize the positive charge, because we do not have any instant where the positive charge is sitting on this particular carbon atom, but rather the positive charge sits on 2 carbon atoms that are flanking that carbon atom connected to the oxygen. So there's no way we can draw a resonance, an additional resonance structure with the oxygen atom donating its lone pair of electrons. That is not possible in this case. So we only have 3 resonance structures with the positive charge distributed on 3 carbon atoms. In the case of ortho, in the case of para attack, we have this positive charge distributed on 3 carbon atoms, but we have an extra resonance structure where the positive charge is also sitting on the oxygen atom. So it means that the oxygen atoms bears a certain amount of this positive charge as well. Now, this is a more stable set of resonance structures because there are many. The more resonance structures you can draw for an intermediate, such as a carbocation, the more stable that carbocation is formed. And therefore, the lower the activation energy that accompanies its formation. And therefore, the faster it is formed. The lower the activation energy, the faster the rate of its formation. And therefore, that is the reason why more carbocations which are corresponding to attack at the para position are going to be formed and lead to the para-substituted product. So as you know, homework, I've not shown the ortho attack, but you go and show the ortho attack and try to draw the resonance structures that will result from attack at the ortho position. You are also going to realize that you are going to have 4 resonance structures. With also the oxygen atom. You can see that one very easily actually. If attack occurs at the ortho position, the positive charge sits directly on the carbon atom connected to the oxygen. So immediately that oxygen can cushion that positive charge by resonance effect. Okay? But also the other pi bond can also shift to that carbon in order to cushion that positive charge. So you are going to, unless I'm mistaken, you are going to get 4 resonance structures also for this one. And then 4 resonance structures for the ortho attack, which explains why substitution with the methoxy tends to direct incoming electrophiles at the ortho or para position predominantly. But we get lesser of the meta-substituted product because the meta-attack will lead to a less stable set of resonance structures. So that carbocation is less stable in short because it has less resonance structures. Okay, so the resonance structure that is actually highlighted here accounts for the selectivity in this case because it is the only one that is different from the others which we saw in the previous slide. So that tends to contribute extra stability. Now, if we look at the carboxyl now, carboxyl attached to the benzene ring, okay? Again, on this one, you can actually remember that carboxyl is electron withdrawing. And remember that I know that even, I want to avoid the confusion here. Even oxygen that is directly bonded to the carbon is electron withdrawing through inductive effect. But it is also electron donating through resonance effect. Now, the resonance effect outweighs the inductive effect. It introduces much more stabilization than the destabilization introduced by inductive effect. Okay? So that tends to, the overall effect of that is that the oxygen will stabilize the carbocation instead of destabilize it. So that is very important, and it's going to be crucial in understanding why the carboxyl is a meta-director. For carboxyl, if attack happens on the meta, this one is a meta-director, that we know. If attack happens on the meta, these are the sets of resonance structures. There are 3 of them. Yes. A question on the ortho para director?
So now, how do we account for the 11% difference between ortho in reference to the one we're talking about?
Okay, so yeah, he's asked a very important question. Very, very important question and very smart. How do we account for the 11%? That is the difference between ortho and para, right? So, go and sit down. I'll give you this as all of you, not just him. Yeah. So all of you, okay? So go and sit down, and then write the resonance structure. So we can even try to go back to understand, to contextualize this question. We can go back to this particular slide. So the ortho is 44%. Okay, the ortho is 44%, while the para is 55%. Okay, so there's a difference of 11 here. That is where you got that figure. 55 minus 44 is 11. Why are these different? Okay, so what I'm saying is, I'm giving you this as homework. Go and sit down, okay? With organic, you will realize how easy organic chemistry is when you sit down. Don't read it like a newspaper. When you do that, you run into serious issues. Rather sit down, indicate, try to draw resonance structures corresponding to attack on the meta, and then draw a set of resonance structures corresponding to attack on the ortho. Then try to compare. If at all some have positive charges that are maybe sitting directly on the oxygen atom, both of these are going to have that positive charge sitting directly on the oxygen atom. But the other three may be slightly different, okay? So go and compare the stabilities of these carbocations. Remember that, more electron withdrawing groups will tend to destabilize the carbocation when they are closer to the carbocation. And more electron donating groups will tend to stabilize the carbocation when they are closer to the carbon bearing the positive charge. So my assignment to you is, go and sit down, draw the resonance structures arising from ortho attack, draw the resonance structures arising from para attack. Then compare them, see if you can see the differences. Okay, if you fail to find the answer, I'll come and answer this in the next session that we are going to have. Or you can still, just come to my office. Then we can discuss. But I want you to get to practice as well. Okay, so organic chemistry is much easier when you practice. Okay, so we were looking at this particular example where now we have a carboxy already that is attached to the benzene ring. If the nitro attacks the meta, we get this intermediate, which is also stabilized by resonance. And we can see that there are 3 resonance structures. So you can see that in this particular case, we are only able to draw 3 resonance structures. And we know that the carboxyl is a meta-direct. So what that tells you is that the carbocation formed as a result of electrophilic aromatic substitution going on at one of the carbons in benzoic acid. This carbocation is not as stable as one that is formed as a result of electrophilic attack occurring on a methoxy substituted benzene. Okay, so we say in this case, you can see that we have 4 resonance structures. So when you have 4 resonance structures, it means that that carbocation is more stable. So the methoxy is an activating group. Apart from being an ortho-para director, it activates the benzene ring system towards electrophilic aromatic substitution. On the other hand, the carboxyl tends to deactivate the ring system because the number of resonance structures we get even when attack occurs at the prepared position, which is the meta position, the number of resonance stabilized structures we get are lesser. So the carboxyl is a deactivating group. It makes the benzene ring system less reactive, but it is still a meta director. So we see this here, that we are only able to draw 3 resonance structures. You can go and sit down and think, okay, and see if you are able to write any additional resonance structure. And don't mistake this nitro to a group that can stabilize the benzene. I hope you're able to see that. Remember from CHE 1010? Yeah. So remember, you learned about drawing electron dot structures. Okay? So electron dot structures, you remember that if you are given a water molecule, okay, so you are given H2O, hydrogen can never be a central atom. Okay, it is always, you know, on the outer side, connected to the central atom, because it cannot accommodate more than 2 electrons. Okay, so you used to do this. You write oxygen, and then you count the number of total number of valence electrons. I'm trying to remind you so that you don't mistake the nitro as something that can contribute through resonance stabilization to the benzene ring system. It doesn't, because the nitrogen does not have a lone pair of electrons, okay, in the nitro. But the nitrogen in amino, NH2, it has a lone pair of electrons sitting on the nitrogen, which can actually be delocalized into the ring system, but not in the case of nitro. So in this case, you used to do this, okay? Oxygen comes with 6 valence electrons. Hydrogen comes with 2 valence electrons for 2 atoms. That is 6 plus 2, that is 8. So you start by distributing those electrons between the outer atoms and the central atom. Okay, so we've used, in this case, 4 electrons out of 8, and we are remaining with 4 electrons. Okay, those electrons go to the outer atoms, but in the case of hydrogen, hydrogen can never accommodate more than 2 electrons around it. It is one of those atoms that defies the octet rule. We know also that it only has 1 s orbital. The 1 s orbital from our quantum mechanics can only accommodate 2 electrons. Okay, so the remaining 4 electrons have to go to the oxygen atom, and this is how we end up with this. We can do the same for a nitrogen atom. A nitrogen atom that is at the center, because it is less electronegative, it has to be at the center. And then we have 2 oxygen atoms, okay, connected to this nitrogen. The most electronegative atoms are connected to the central atom, are connected to the central atom. So we have 2 of them. So we can include the carbon atom. A carbon atom is the one that is attached to the nitro. Okay, but we can imagine this as something that contributes 1 electron, because it is also attached to something else. So we distribute electrons around the carbon, between the central atom and the outer atoms. We get this. Nitrogen comes with 5. Okay, first of all, let's understand this. 5 plus oxygen, that is 12. Okay, 6 plus 6, that is 12. Okay, and then plus 1 from the carbon. I'm using 1 because it is the one that is involved in bonding to the nitrogen. The other 3 are involved in bonding to other parts of the molecule. Okay, so plus 1 from carbon, which gives us 12 plus 5, that is 17, plus 1, that is 18 electrons. So we have 18 electrons to distribute. So we are going to put these in between. And then we have 1, 2, 3, 4, 5, 6. 6 electrons used already. 18 minus 6, that gives us 18 minus 6, that gives us 12. Okay, so we have 12 electrons to distribute, and the best way to distribute them is to actually put them on the outer atoms. That is the next step. Whenever there are any electrons that are remaining, you put them on the outer atoms. Okay, so we put these 6 on the oxygen atoms. The carbon atom is already an octet structure, because remember that it is bonded to something else. So it already has 1, 2, 3, 4, 5, 6, 7, 8. This is why I'm not considering it. So I've distributed those electrons around the oxygen atoms. But nitrogen still has a shortage of electrons. It doesn't have 8 electrons. It has 1, 2, 3, 4, 5, 6. Okay? Now, when nitrogen has 6 electrons, it is not an atom that is able to defy the octet rule. It already, it has to satisfy the octet rule. So one of these lone pairs of electrons, in order to even minimize the formal charges, has to form a double bond with the nitrogen. So this lone pair of electrons can shift. When that happens, we have 2 pairs of electrons between the nitrogen and also the oxygen. And therefore, the structure of the nitro is like this. We have nitrogen that is connected to an oxygen atom. This oxygen atom has these lone pairs of electrons with a formal charge of -1. And then this is connected to an oxygen via a double bond with 2 lone pairs of electrons. Then this is connected to a carbon that is connected to something else via a double bond and a single bond. So you can see there's no lone pair on the nitrogen. So don't mistake nitro. Nitro can never donate a lone pair of electrons via resonance effect into the ring. It can't. But the NH2 does that. So the NH2 does that, and this is the reason why you see that the nitro is actually does not know there's such an effect. We are going to see that even when it is attached, instead of the carboxyl, you have the nitro. Don't ever think that there's a lone pair of electrons on the nitrogen. It's not there. I've shown you that using CHE1010. So you should never, write resonance structures with a lone pair coming from the nitrogen, because it is not there. But when you have when you have an amino, NH2, that has a lone pair of electrons on the nitrogen. And that is able to stabilize the carbon via resonance effect, the same way that the oxygen has. Okay, so here we have 3 resonance structures which corresponds to attack on the meta position. Now, what if attack was to happen on the para? Okay, now this is unfavorable. What if attack was to happen on the para or the ortho position? Now this is unfavorable. Okay, and it leads to a minor product. Although we have 3 resonance structures here, which is the same number as in the previous one, same number but not identical, we actually see that there's one disfavored structure here where the positive charge is sitting on a carbon atom connected to an electron withdrawing group. The carboxyl is electron withdrawing. It has no capacity for electron donating in form of resonance stabilization because there's no lone pair on the carbon there. So there's no opportunity. For oxygen, we saw that the lone pair on the oxygen was able to actually cushion that positive charge, but this is not the case here. So this resonance structure is highly disfavored, and it is a significantly lesser contributor because this positive charge is less stabilized. It is sitting on a carbon atom. Whenever you have a carbocation with the positive charge sitting on a carbon connected to electron withdrawing groups, that is destabilized. Okay, a carbocation will be stabilized when electron withdrawing groups are connected to that carbon that has a positive charge. In this case, we see carboxyl, which is electron withdrawing as a result of the electronegativity of oxygen atoms connected to the carbon. That tends to destabilize this resonance contributor, and therefore is a lesser resonance contributor. Effectively, we can say the most important resonance structures here, which are stable to a substantial extent, are only the first one and also the third one. So we see that this set of resonance structures are unstable, or this set of resonance structures are unstable compared to the other set of resonance structures where attack occurs at the meta position. Here we do not have any positive charge sitting on a carbon atom connected to a carboxyl carbon. We don't have that. So these are more stable. These are more stable sets of resonance structures. And this explains why attack occurs at the meta position whenever you have a carboxyl connected to a benzene ring system. The incoming electrophile will predominantly go to the meta position. If it goes to the ortho or para, then we get this highly unstable contributor, which is this one. You can also do the same and try to do the attack. Try to go and do the attack. This is now, I've not shown that, I think. You can go and try to show what set of resonance structures would arise if attack was to occur at the ortho position. You are also going to come to the same conclusion with the positive charge in one of the resonance structures sitting on a carbon atom connected to a carboxyl carbon. That is very destabilizing because the carboxyl is electron sucking by virtue of the oxygen atoms that are attached to the oxygen, to the carbon atom. Okay, so even for the nitro, okay, I've not shown the nitro, but if the nitro is present, let me just try to show it in an explicit way here. I've not shown the nitro. Supposing we have a benzene ring that has, instead of carboxyl, it has nitro. Okay, and I'll try to write it in an expanded fashion in this way. And then oxygen, and by the way, the nitrogen has to, with this formal charge, even the nitrogen has to possess that +1 formal charge. So there's +1 formal charge, and then -1 formal charge on the other nitrogen. If the electrophile comes, and then attack happens at the ortho or para position, you are going to have an intermediate with the positive charge sitting on this carbon atom. Now, don't think that that positive charge will be stabilized by your imaginary lone pairs on the nitrogen. They are not there. There are no lone pairs on the nitrogen atom. Just go back to CHE 1010, drawing electron dot structures. You realize that the nitrogen actually has a formal charge of +1, which tends to make it quite electron poor, and therefore it doesn't have that lone pair of electrons to donate. In order to stabilize the carbocation that is going to be formed. So therefore, the nitro is also a meta director. It's not a para or ortho director. You can go and try to practice more with the nitro and see if you're able to get the same set of resonance structures as is the case with the carboxyl. But bear in mind that you need to be careful with that one because nitrogen does not possess a lone pair of electrons in this particular case. Okay, so with that, we can try to now talk about, I mentioned this briefly, that when you look back at this, let me just take you back to this. So when you look at this, we see 4 resonance structures, meaning a more stable carbocation is formed. Okay? But at the same time, you can equally draw, we can equally draw some resonance structures of methoxybenzene, and we can do this by doing this. Okay, we have CH3 and then connected to an oxygen atom that is connected to a benzene ring system. Okay, I'll show you the first one, then you can go and finish the others. This one as these pi bonds. So remember that they are electron lone pairs on the oxygen. Okay, this is one, strictly speaking, this is one resonance structure. It's not a hybrid. Because we also know that we can draw another resonance structure, although it's a less contributor, but it's still a resonance structure of methoxybenzene by the lone pair forming a pi bond. Then once we kill that lone pair, we generate another one by putting another lone pair there on the carbon. And then that tends to form the next resonance structure with the lone pair now being moved to that particular carbon atom. And then this pi bond is maintained, that one is maintained. Then a double bond exists between the oxygen and also the carbon. And then a positive charge is there. You can continue now from here, okay? Other resonance structures that you can draw. You see that the ortho position has a negative charge. Okay, I can show you the next one. So we have this lone pair now. We can kill it by forming a pi bond like this. And then once we do that, this forms a negative charge on this carbon atom. And what we are going to have is a ring system that looks like this. Oxygen, and then a methyl. And then some lone pairs of electrons, and then a double bond there, and another double bond there. Okay, so, and then a positive charge on the oxygen atom. So, the reason why I'm showing this is, looking at the stability of resonance, looking at the stability of the intermediate cation is not the only way to explain why methoxy is ortho and paradirecting. Okay? The other way to explain why methoxy is ortho and paradirecting is to actually draw resonance structures even before attack occurs. You see that the ortho position has a negative charge, meaning it is more nucleophilic. It will be attracted to the electrophile more. Even the para position has a negative charge. Now, when you go home, you can continue writing resonance structures and hope to get other resonance structures where the negative charge is sitting on the metacarbon. You are never going to get them. You can do that until the end of the semester. You are never going to get those resonance structures where the negative charge is sitting, or the negative HOMO charge is sitting on the metacarbon atoms. You are never going to get them. Okay? In this case, if you move this, the negative charge, or if you move this lone pair of electrons like this, and then this one moves, the negative charge goes to the ortho position. So because we see that in all resonance structures, you can try to go and practice as much as you can. If you are not convinced, go and try to draw more resonance structures. If you are drawing them correctly, you are never going to have one where the negative charge is sitting on the metacarbon. You can try that until the end of the semester. You are never going to get those. So this is another way to explain why the methoxy is an orthoparadirector, because we can see that in other resonance structures of this neutral molecule, the negative charge is actually sitting on ortho and para carbon atoms. So those are going to attract the electrophile more than the meta carbon atoms. So that is very important for us to understand. And now, this actually also gives us an opportunity to explain why the methoxy itself is an activating group, because it enriches the ring system. You can see that the ring system has a cloud of negative charge because of those negative charges that are sitting on the ring system. So that tends to activate the benzene ring system. So methoxybenzene, for example, if you carry out nitration with methoxybenzene, it will react faster than nitration carried out with the benzoic acid, because the methoxy group itself tends to activate the ring system. We can't draw these resonance structures from, in the case of benzoic acid, because there are no lone pairs sitting on the carbon atom, which is part of the carboxyl. So we can't even start shifting electrons from there. So the carboxyl does not activate the ring system, but instead it deactivates it, because it is electron sucking. In terms of inductive effect, it will deactivate the ring system, and therefore the ring system will be less nucleophilic in this case. Okay, now that is going to help us in explaining why, when you see on this slide, activating and deactivating effects, any resonance effect which I've shown there for the methoxy, that also applies when you have an hydroxy group attached to a benzene. It also applies when you have an NH2. Every time you have a group that has a lone pair of electrons on the atom, directly bonded to the carbon atom, there is potential for activation of the ring system via resonance, because you can actually draw other resonance structures which actually show that the ring system actually has negative charge, which tends to attract electrophiles more than a ring system that doesn't have this negative charge. So we have NH2. So NH2, and then OH, and then O attached to an alkyl group. Okay, so these are potential for resonance effect. And therefore, they are able to delocalize the positive charge on the cation intermediate, but also they are able to contribute negative charge into the ring system. And that lowers the activation energy for electrophilic attack. Okay? And that tends to lead to the formation of the product much faster. So the formation of a product where the nitro is the electrophile, and then also the nucleophile is methoxybenzene. That methoxybenzene will react faster than benzoic acid that is being substituted with the nitro. So if you have nitro, cyano, and then carbonyl, and then sulfuric acid, these do not have lone pairs of electrons sitting on the nitrogen atom, and therefore there's no resonance effect. In fact, this is wrong. I hope you saw that. When I say here that any resonance effect, first of all, any resonance effect such as that of nitro, this doesn't make sense. Okay? Any resonance effect such as that of nitro, well, there is no resonance effect arising from nitro. Nitro cannot donate electrons to electrons to the ring system, okay? But rather it sucks away electrons from the ring system, okay? But we can have resonance effect. We have resonance effect coming from the ring system to the nitro. That is possible. Probably this is what I meant, I think, here. And resonance effect, but I think this needs to be reworded to avoid confusion, because some students may think that the resonance effect is coming from the nitro. No, okay? The resonance effect is coming from the ring system itself. So look at this example. So this pair of electrons, these pi electrons, can actually move and form a double bond between the nitrogen and the carbon. And then, don't break this, because now you are going to take away the oxygen atom. Don't do this. So resonance structures will not break, bonds to form separate atoms, which are separated from each other. But what moves are electrons in pi bonds. So the one that is likely to move is this one, to form an extra lone pair. Now, you can see that this resonance effect is sucking away electrons from the ring, thereby deactivating it further. So this is what we mean when we say any resonance effect. We need to reword this so that we avoid thinking that the resonance effect we are talking about is resonance contribution that comes from the nitro, but it is rather resonance contribution that comes from the ring itself. And that tends to, it deactivates the ring towards further electrophilic substitution. We have other groups, such as the methyl and alkyl groups. These release electron density towards the ring. The same way, remember that we talked about hyperconjugation in the carbocation that is formed during SN1 reactions. And we said third-degree carbocations are more stable because there is actually more hyperconjugation, which is the partial overlap of sigma bonds sitting on the carbon, the methyl carbon, the sigma bonds between the carbon and hydrogen, the partial overlap of such sigma bonds with the empty p orbital that has the positive charge. That is what we call hyperconjugation, and I remember demonstrating it on the board here. This also happens when we have methyl groups. Methyl groups, they do not have resonance effect, but they have hyperconjugation, which results in the electron releasing effect in form of the plus I effect, not minus. Plus I is electron releasing through sigma bonds, while minus I is electron withdrawing through sigma bonds. That also, methyl groups, alkyl groups, other alkyl groups, ethyl, propyl, butyl, tertiary butyl, those tend to activate the ring towards further electrophilic aromatic substitution. Then we have other derivatives such as those containing, nitrogen that has been alkylated 3 times. In that case, this is an example of an ammonium ion, which is a derivative of an ammonium ion. Now, the ammonium ion does not have any lone pair of electrons sitting on the nitrogen. It's like the nitro. The ammonium ion has already utilized the lone pair of electrons by forming a dative bond or a coordinate bond with the hydrogen. So it doesn't have any lone pair. It's not basic. It's not necrophilic. In fact, it's acidic. So even in this case, NR3 with a plus, that is a derivative of an ammonium ion. It can't be electron releasing. It can't be electron donating via resonance effect, but it has a minus inductive effect from the ring, okay, withdrawing electrons from the ring, which decreases electron density on the ring and deactivates the ring towards further electrophilic aromatic substitutions. Okay, so these are just some of the generalizations that we should you know, these are the take-home kind of general principles from what we've learned. Alkyl groups, a phenyl group, because it has pi electrons. Okay, if we have a phenyl group, which is a benzene, supposing we have two benzene rings, instead of this being attached to a nitro, this is attached to another benzene. That is also electron activating, because it has electron pairs in form of pi bonds, which can be delocalized into the next ring system, thereby activating it. So the alkyl groups, and then also the phenyl groups and other substituents in which the atom that is bonded to the ring has an unshared pair of electrons. These are ortho-para directing. Okay, so we've seen the reason why by looking at these principles structurally. And then all other substituents are meta-directed. We have a substituent that doesn't have a lone pair of electrons sitting on the oxygen directly bonded to the benzene carbon, and it's not benzene rings itself, then that particular substituent is meta-directed. Okay, so that is very important, and we know why this is the reason. So ortho-para directing groups, except halogens, are activating. Okay, halogens are ortho-para directors. Now we are going to see the reason why. Remember that we've talked about electron withdrawing groups. Chlorine and also bromine are electron withdrawing groups. They are quite electronegative. Okay? If they are quite electronegative, why are they ortho-para directors? We are going to see that they are ortho-para directors as a result of the resonance effect also, just like the oxygen atom. Okay? But they are weaker. In terms of reactivity, they react much slower compared to oxygen substituted benzene rings, because they are electronegative. Okay, so they tend to decrease the electron density in the ring system by the electronegative effect. Although they also have the electron withdrawing effect, but their electron releasing effect through resonance is not as strong as that of oxygen. Electron donating effect via resonance of halogens is not as strong as the electron donating effect via resonance of the oxygen atom. So they are less reactive. The oxygen attached to the benzene ring will be more reactive. So this is why we are saying the halogens are weakly deactivating. They deactivate the ring system because their resonance activation into the ring system is not as strong as that of oxygen. Okay, so that is very important for us to understand. And for the halogens themselves, the inductive and resonance effects run counter to each other, but the former is somewhat stronger, which is the inductive effect for the halogens. The inductive effect, the capacity to attract electrons via inductive effect or via sigma bonds, that tends to be much stronger than the resonance effects. And therefore, that is why they are classified as deactivating. But the net effect is that they are deactivating, but still ortho-para directing, because they can also stabilize this carbocation in this manner, the same way that oxygen was able to stabilize the carbocation. Okay, that is what I'm showing there. Okay, so this marks the end of this particular topic, and we are good to go for the exam. I'm going to prepare some more tutorial sheet questions so that you can practice. And I would like to advise you to solve those tutorial sheet questions. Don't solve them in your mind. Rather sit down, like I've been emphasizing. Sit down and solve them. Yes, okay. If we still have some time, so we still have about 30 minutes. So I can accommodate some questions if there are any on this particular topic. Can we keep quiet so that we can utilize maybe the next 30 minutes? Okay, yeah, that's a very genuine, I think, concern, because I know you guys are about 1,040 from the records I saw from the head of department, but I never got even 500. I think the highest I got maybe was 300 using Big Blue button. I don't know whether the others, is it challenges signing in? So I'm told you sign in, then you are logged out. So yeah, that's very unfortunate. So now I don't know how we can do this, because next week we begin. Or other courses you are continuing with lectures. Okay. Okay. We'll address that. You have a suggestion?
Exams start on the 13th.
Okay, can you keep quiet so that I can hear what you said? We'll address your question of this. Yes. Okay, let me find out. I've been getting this question from a lot of students. Let me find out from the assistant dean for School of Medicine. Then I'll post that information on Moodle so that everyone is aware. But the standard, I would advise you to get ready for June. Because the standard is, the standard, so normally the standard is to write these exams for the first semester courses, to write them at the end of first semester. There were some disruptions in the previous maybe 2 academic years because of COVID-19. So students were allowed to write at the end, both if they are taking 2 half courses. Okay, one which is a prerequisite of the other taken in the first semester. They were allowed to write both of them at the end. But that wasn't, it was necessitated by COVID-19, I think. So normally, when we teach a first semester course, the exam is administered at the end of the first semester, not at the end of the year. So I would advise that you get ready for June, this month. You might write the exam. But I'll clarify that. I may be wrong. I will contact the assistant dean for School of Medicine to find out. Then I will send a clarification message. Okay, so yes.
I wanted to ask on the same issue that you've addressed. When exactly are we going to get the feedback?
The paper?
No, the feedback.
Or the feedback from the test?
No, the exam.
Or from the exam? Yeah, so the idea is before the beginning of the second semester, you're supposed to get feedback because there are some courses which are prerequisites to some second semester courses. So ideally, we are supposed to mark them and then give you feedback before the beginning of first semester, before the beginning of second semester. But we'll clarify, what is going to be there, because this course is just a standalone course. There's no second semester component. Okay, so, okay, before you, this gentleman. Okay, yeah, some of these questions, of course, so he's asking if someone gets a D+ in a certain course, but I don't see the reason why you should get a D+. Yeah, you should never prepare for it. You should never prepare yourself for a D+. What you should always prepare for is prepare yourself for the best. Okay, don't start, in the event that I get a D+. Okay, to answer your question, some of these questions are beyond myself. I don't know when supplemental, because these are set up by, I think, Senate. Yeah, they come up with a timetable. And then a timetable will be put up. So I don't when a supplementary exam would be given. Okay, that gentleman. If you score below 50% for the CA, you are not going to sit for the exam. For this particular course, that is supposed to, although we've rarely enforced that, but there are some schools that enforce that. I can enforce that if I want as well. Yeah, but I'm not going to enforce that. Yeah. Okay, so any other questions? Test 2. You want test 2? Okay. So now I'm not sure, because others are saying yes, others are saying no. Okay, so here is the thing. Okay, so when you look at the course outline, even the test, that test I prepared, which was administered maybe some few weeks back, it was written, I think, test 1, right? Yeah, so the implication is that there's going to be test 2. Yes. Not online. Okay, so if there are no, I was expecting people to ask questions to do with what we've learned. But again, the last one. Okay, relating to what we've learned. Okay, so. Okay, where exactly? So let's get to hear what he has to ask. If you look at what? Uh-huh. 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 Okay, 2,4 dinitrophenyl hydrazine. Okay, so your question is when it was being made, right? Or maybe when it reacts, when it was being made. Okay, now there may be different steps that were followed. Probably if it is 2,4 dinitrophenyl phenylhydrazine. Remember that the hydrazine itself is orthoparadirecting. Okay? So if the hydrazine is orthoparadirecting, it's likely that the reaction was carried out in excess over the nitroelectrophile, which substituted both positions, ortho and para. So you are right. It is possible that when it was being made, when you make 2,4-dinitrophenylhydrazine, bearing in mind that the hydrazine itself is orthoparadirecting, those nitro groups will go to the ortho and para, and hence 2,4-dinitrophenylhydrazine. Yeah. So now we can. Yeah, I like the way you made sense out of that particular molecule. So we can now make sense out of these molecules. Even you are going to find that even drug molecules have such functional groups at some of those positions. You are going to understand. If you can take a look at paracetamol also. Paracetamol is made from phenol that reacts with nitric acid and sulfuric acid. And then because we know the hydroxy is orthoparadirecting, we are going to get both the ortho and para compounds. Then we isolate the para. And then once we isolate the para, we reduce the nitro to NH2 and then carry out substitution with acetic anhydride to get paracetamol. Okay, so any other questions? What time is this? So now, she asked a question about having physical lectures with, that one is difficult for me to, because I have to start, in fact, this week I started teaching first year students. Okay, so my schedule is going to be quite tight, but what I encourage people to do is, come to my office, and as long as you are a 2505 student seeking help, because I know the challenges we've had. Okay, come to my office. As long as I'm there, I'm not even going to say I'm busy. If you have anything to ask, then I'll create time with you and try to guide you so that I demystify some of those things that we are taught during online. Otherwise, I could have considered your request to organize physical lectures. But just this week, I started teaching first year students as well. It's quite hectic. I'm taking 3 lecture groups. You have to have 3 lecture sessions per week for the 3 of them, which means I have to have 9 lectures in a week. That is going to affect my capacity to organize makeup sessions. But feel free to come to my office. Okay, room 325 on the 3rd floor, Department of Chemistry. Yeah. Okay, I think we can end here. So all the best.
There are people who are still here trying to get that.